So this is forthcoming in NeurIPS this December, and this is joint work with Taylor Lundy, who is a graduating PhD student at UBC. So I am going to assume that a lot of you are just theory people and don't have a mechanism design background. Is that right? Okay, cool. So let's just do a little refresher about like what is mechanism design. So I'm going to assume you all know what algorithm design is. So algorithm design, we have some input instance, some input data, and we have some output outcome, and we're trying to maximize or minimize whatever our objective is, maybe revenue, efficiency, whatever, okay? Specifically today, I want to talk about allocation algorithms. So we're specifically deciding who gets what. Okay, why is mechanism design different? Instead of just having an input instance, input data, we're talking about data when it's reported by strategic agents who have a stake in the outcome. Okay, that's the main difference, which means that we need to reason about the fact that they're strategic when we're deciding who gets what. Okay, if we have, for example, some health insurance providers, Aetna, Sigma, Kaiser Permanente, and they report to us their data and say, for example, our objective is to pick the provider that has the minimum cost. If they're just telling us a number, we would just say, okay, great, give it to Kaiser. They could tell us whatever cost they want. They could just lie. We're just picking the minimum. If they want to get picked, they could say whatever number they want in order to get picked, right? They know we're just trying to pick the minimum. They're telling us their data and they want to get picked. They'll tell us whatever they want. Make sense? So in order to make sure that they're telling us true data so that we wind up actually picking the one with the true minimum, we're going to decide who pays or gets paid what in addition, and there is some price such that this will incentivize things properly. I'm not going to talk about those details right now, but the basic idea is that we're going to use game theory to reason about incentives within the algorithm in order to guarantee optimality or approximate optimality. Because this data is not random, it's strategic. It behaves in a predictable way. It behaves according to some game theoretic model. Okay, so we know that our strategic agents are maximizing their utility functions, and we know what their utility functions are, so we can predictably reason about what they're going to do based on information we have. That's the very high-level idea. Does the high-level idea make sense? Okay, so if we look at this in the most basic setting, what we usually talk about is like if we're having an auction with n bidders in one item, if we want to, for example, give the apple to whoever has the maximum value, that's what maximizing social welfare is. We want to give it to the person with the maximum value. What we're trying to come up with is an allocation rule, X. The allocation rule takes in our input data and just gives it to the person with a max. So for whoever has max, it gives a 1, and for everybody else, it'll give a 0. Okay, that's the allocation rule. Make sense? Okay, but if again, they can just say numbers, it'll give it to whoever says the highest number. And again, they want to get the apple. So it'll just give it to whoever says 5. But the problem is these values are private. People have to tell us those values and they can lie about them. And so what we do is we need to come up with a payment rule in order to charge people for the apple so that they tell us their true information. That's the challenge here. Okay, so the payment rule will also take in this information of what people are reporting. In addition to deciding who gets the apple, it'll decide how much they pay for the apple, such that it'll be in their best interest to report their true information. Make sense? Okay, and so overall, they will maximize their utility, which for example, X will be 1 if they get the item, so they'll get 1 times 5 for the person who gets 5, minus how much they have to pay for the apple. So they'll want it if they get some positive utility, otherwise they'll get like 0 times their value minus how much they have to pay, and so they'll get negative utility. Does the high-level setting make sense before I get into details? Okay, so what I'm going to study today is a Bayesian utility maximization problem. Okay, so let's talk about the setting again where we have n buyers and 1 item. And each buyer is going to have a value drawn from some prior distribution, and I'm going to assume right now that they're all IID. Okay, so all these values are drawn from the same distribution. My objective that I'm focusing on today is going to be utility maximization. So that is just going to be the sum of the buyer's utility added up for all of the buyers. Okay, so probability of allocation or deterministically allocated. This can be a probability, by the way. I was talking about it being deterministic before, but it can be a probability times their value for the item minus what they have to pay. Okay? And our goal is to design a mechanism to design that allocation rule and the payment rule such that it is truthful and such that we maximize this function. So we want to get the real data and maximize this function. Why does it have to be truthful? There's something that says it's without loss to design truthful functions, and then we know for sure we can maximize this function. Okay? Make sense? Yes?
Sorry, can you tell me again, how do you calculate this PI?
How do what?
How do you calculate this PI again?
Okay, so that's part of the challenge, is to come up with a PI to make things truthful. There is a theory that says that when you're only dealing with one item, or in the single parameter setting, which is slightly more general, that there is just a formula to come up with a PI based on the X such that everything is truthful. And I'm sort of skirting over that because there's just a formula of X that makes everything truthful. But there is a P that makes everything truthful. When it's multidimensional, when there's multiple items, it gets more complex. But that's part of the design challenge, right? You have to come up with a P such that together your X and your P incentivize people to want to tell the truth. That's like, if you were formulating a linear program, that's a constraint on your linear program. Okay? Yeah?
I think you sort of said this, but is the expectation only over the valuation draws, or can the mechanism, like the assignment mechanism, also be randomized and the expectations over that?
Yeah, the assignment can also be random and the expectations also over that. Thank you. Yeah. Other questions? This is great. Please do ask questions. Okay. So this is called utility maximization. It's also sometimes referred to, it has a lot of names, residual surplus, consumer surplus, money burning, or deals. Okay, why is this our objective? Oftentimes we just, let me use my mouse. We often just maximize this first part of the term, which is welfare. And this is basically just give it to the person who wants it the most. And we don't worry about these minus payments. The reason we don't worry about these minus payments, the logic is when they're payments, they stay in the system. So sure, the users pay them, but they go to the sellers. So we don't need to worry about how much people are paying because the welfare of the whole system factors in the payments. So if we're maximizing the welfare of the system, we only need to maximize the first components. Okay, so when we might want to maximize this objective is, one, when we care about the buyers in particular, or two, in systems where these payments don't actually get transferred. Okay, so here are some examples, and these are examples that specifically refer to why we might call it money burning or ordeals, is when these payments are burnt, they are not transferred, or they are ordeals that people need to go through as opposed to monetary payments. So for example, it might be waiting in line for ER visits or affordable housing. That's a way that you pay for things that is not a monetary payment, and it doesn't benefit anyone. It's just used as a form of payment. Bureaucracy, you need to fill out paperwork for food stamps, you need to fill out paperwork for grant proposals, for example, and that doesn't necessarily benefit everyone, it's just used as a form of payment. Proof of work systems and cryptocurrencies, medication step therapy, you have to fail a bunch of medications in order to show that you can get a more advanced medication. For example, in Lyft Wait and Save, you pay with your time in order to get a cheaper option. Okay, so when you're paying with your time or with bureaucracy, or you're paying with these ordeals, that does not get transferred and benefit the seller. And so that might go into the objective function that it's just not benefiting society, okay? And so we should factor that into our design. Does the setting make sense? Okay, yes?
Probably have some constraint on payment. What's preventing, because the payment can be negative here, right? So what's preventing you from?
Yeah, payments need to be non-negative.
Non-negative. Okay.
Yeah, sure. We don't, I mean, if you think of it as like an ordeal, like bureaucracy and wait time, you can't give them, yeah. Okay, so let's talk a little bit more about this utility objective. If we look at it, you'll notice that it breaks down into the two most common objectives in mechanism design, okay? So the first objective is welfare. As we said, this is the welfare of the system when the money stays within a system. We know very well how to maximize this objective. This is probably the most studied, most completely studied objective. And the second one is revenue, where we just want to maximize the payments in the system and expectation. Okay, so what do we know for these? For welfare, we just want to give it to whoever values it the most at whatever prices are necessary. Okay? And this is completely solved. Let's just talk about the single item setting with the second price auction. Okay? We completely know how to do this. The second price auction gives it to the person who values it most at a second price. It's truthful. Great? Okay. For revenue, what you want to do is you want to balance using high prices with the probability of sale, because if you price it too high, they won't buy it. You do this nice balancing act. You get what turns out to be this really nice characterization, this whole theory of virtual second price with reserve that we've known since 1981, won a Nobel Prize. Okay, so this is solved. Yes?
Wait, sorry, so aren't we trying to minimize revenue here, though? So
Yeah, I'm just trying to say that like it's a convex combination of these two, it's a combination of these two objectives which are well known. But yes, we're trying to trade off these two things. Okay, but I want to show you why utility is so much harder. So let me go through a couple examples. So in this first example, let's say that we have 3 bidders with values 100, 2, and 1. Okay, so the person with the highest value who we'd like to give it to has a value of 100. But in order to give it to the person with a value of 100, we have to set a price so that the other people are not buying the item. Okay? And so the price that we would set in this case is a price of 2 to make sure that the buyers with values 1 and 2 are not buying it. Okay? So what that means is that the utility of the buyer would be 100 minus 2, which is 98, which is very good. Okay? In this case, that is optimal. Okay? So that is right here the second price auction. So that works. Giving it to the highest buyer at the second price is the optimal thing to do here. However, in the next example, say we have 100, 99, and 1, if we were to do the second price auction, we would have 100 minus 99, which is really bad. What could we do in this case instead? Sorry?
Can you split the item?
You can't split it, but you can randomize. Yeah, so you can set a price of 1 and then randomize between who you give it to, between the top 2 bidders, right? And this is optimal in this case. So your expected value is, just under 50 and minus the 1 of the payment. Okay, so you get 48.5, right? Or 0.75. Make sense? Okay, so second price auction is not good here. What you want to do is set a price of 1. Does that make sense? Now, in this example, what should we do in this example?
Give it random.
What is it trying to optimize from whose perspective?
Utility. Aggregate utility, yeah. Yeah? Yeah, exactly. So just give it away for free at random. Exactly. So here you just get the expected value of these 3 bidders, and you don't have to subtract off any payment because you gave it away for free. So, okay, I know the prices worked out to be very close to each other, but they're actually very, very different examples. This first one was a second price auction, where the second price, if you just say always use the second price auction, our second price could be as high as 99, just right less than the first price bidder. Okay? In this third one, we're saying always set a price of 0 and give it away for free, always get the expected value. So clearly these are very different mechanisms, and what you should do really varies depending on your example. Okay, now I'm cheating a little bit because I'm showing you exact instances, and we should be maximizing an expectation. We should have distributions, but maybe they're point masses or something, okay? Make sense? Okay, so what should we do? We need to do some sort of balancing act between who values it the most and what the lowest prices are. We need to somehow give it to who values it the most, or the group of people in expectation who values it the most, and not charge too large of a price. And it turns out at the extremes, it's either the second price or the lottery, and kind of interpolated in between. It turns out it's actually a theory very similar to a Myersonian theory that is adjusted for this setting, but I'm not going to go into it right now. Okay, and this is completely solved for the one item, actually the single parameter setting in Hartline-Roughgarden 08, which I'll talk about more in a second. Okay, but what I want you to get from this slide is that utility feels very different from welfare and revenue, which are the two objectives that we've studied, even though it is equal to welfare minus revenue. The design problem, just so we're clear, you're trying to maximize this objective, set the allocation and the payment subject to incentive compatibility. So we want to prefer to report your true VI, that's incentive compatibility, over any other possible V prime I. You want it to be individually rational, which means that you prefer to participate as opposed to not participate. You should always get non-negative utility from participating. As it can be 0, just it shouldn't be negative. And then actually, my animation appears too early, is that what I'm going to study today is the matching setting, not just the single item setting. So we're going to have a bunch of items where we're trying to match them. And so we need 2 more constraints, which is item feasibility. We can't allocate any item more than once. And unit demand feasibility, which says that each bidder receives at most 1 item. So really just that it's a matching, okay? At most a matching. Not everybody has to be matched. Yeah?
What's the motivation for like wanting truthful mechanisms for whatever the first thing is, if like really all we're trying to do is optimize welfare minus revenue?
Okay, good. So either way, I claim, we need to worry about people's incentives. Because if people will lie, they're not going to report this V. So this function will be like xi of b times vi minus pi of b. And that b is a function of v because they're strategizing predictably. Okay, so I need to maximize this as a function of the b's, the strategic b's. Okay, but if they have, there's something called the revelation principle, which I will say very quickly, but is actually a little bit more nuanced. But basically, if they have some strategic B, bid, that is a function of their V, what I could basically do is simulate that for them by saying, I have all the same information as you. All you know is your distribution and your value and everybody else's distributions. I also know your distribution and everybody else's distributions. If you tell me your value, I will simulate your bid strategy for you. So I might as well require a truthful auction where I apply that strategy for you and build that into my auction. Okay, this is the revelation principle. If you didn't follow that, that's okay, but there's basically a black box proof that says it's without loss to require truthful mechanism design. Either way, we need to, in our analysis, account for the fact that people are going to be strategic. You can't just say they're reporting whatever. You either need to say they're reporting something else and I need to guarantee outcomes for that report, or I will force them to then report the truth. And therefore, I definitely am guaranteeing outcomes. Yeah?
You were saying that if they report some other B, you would optimize over that B. Why didn't you just optimize over the initial B for the utility function?
I am optimizing over the V, and I'm forcing that it is in their best interest to report V. What I was saying is that if they want to report some other B, which is a strategic function of their, like if I didn't require them, if I didn't have this first constraint, then they might want to report some B, which is a function of V. And I'm saying I can create a new mechanism where I just apply B to whatever they tell me. And now it's in their best interest to report V. Is there a board? Can you see here?
There's a kind of
Oh, here. Good.
this rolly board.
All right, you can see here, right? Like if you have some mechanism where they want to report some B of V, what I can just do is like create a new mechanism around it where I apply B for them. I apply B to whatever they tell me. And so now they're going to want to report V. And I'm giving the same outcome. This has some outcome. I'm giving the same outcome.
You're optimizing the utility for the B in the output.
For the input, yeah.
But I thought like you wanted to optimize the utility for the inner B.
Uh-huh.
The reported B.
Yeah. For whatever the report is. In this mechanism, the report is going to be V. In this mechanism, it would have been B. We can talk about it offline. Yeah. This first constraint means they're only going to report V, so I can just optimize in terms of V. If I didn't have that constraint, I would have to worry about it. Okay? Other questions? Yeah. isn't necessary to leave buyers unmatched in order to satisfy these constraints.
Or even both the buyer and an item.
To satisfy these constraints and maximize. So that is one thing I'm going to talk about today, yeah. So that's one of our results, yeah. Okay, so our setting is going to be this matching setting, but specifically it is going to be an IID setting. So buyer I has value Vij for each item j, and everything is IID across both n buyers and m items, okay? And the reason for this is because it's sort of the natural generalization of what was studied in Hartline Roughgarden 08, where buyer I had value Vi for each item j. Okay, so there were n buyers and m identical items. So they only really had one value Vi for each of the items. So you should think of this as m apples as opposed to now we have m fruits, and they're different fruits. Okay? Still everything's IID, but it used to be just apples, and now they're different fruits. Cool? Okay. So what do they show in the seminal paper, Hartline Roughgarden 08? The reason it's abbreviated is just because I refer to it so many times. So first off, they come up with this sort of optimal Myersonian type analysis, which is like a virtual value type theory, if you're familiar. They also come up with a really nice prior free mechanism and benchmark, which means that when they don't have the prior distribution F, they're still able to approximate it in the worst case without any Bayesian distribution. And then they show that the gap between optimal welfare, so when we just have the xi vi, versus optimal utility, when we're subtracting off these payments that have to be incentive compatible, is theta 1 plus log n over m, where, again, n is the number of buyers and m is the number of identical items, and that this is tight. Okay. What else is known in the setting? There's also a paper from 2016 by Fotakis, Tsipras, Samos, and Zampatakis, which shows that there is an m log n approximation for the unit demand setting. So I've translated that to the unit demand setting, but their paper is actually general for any set of outcomes. And what I will show today is that we have a tight 1 plus log n over m approximation for the IID unit demand setting. So this matches the bound for the setting when they're all apples to now when they're different fruits. And then this has since been improved to a 1 plus log n times c over m bound for unit demand more generally beyond just IID when there is this condition that sort of parameterizes unit demand in a way. It's called the C superstar condition, and it basically says how far away your preferences are from your favorite. Okay, I'll talk about that at the end. Cool? Yeah.
Just to make sure I'm parsing this correctly, so like this ratio of welfare to op utility is not saying that for any particular random draw evaluations, the gap between welfare and utility is bounded. It's just saying an expectation over all the draws.
Exactly, exactly. So the idea is that we don't know what optimal utility is. It's really hard to know what the optimal utility mechanism is. I'm going to talk about that in a second. And so we don't really have a good upper bound yet. And so the only real upper bound we have is just the optimal welfare mechanisms. And so that's what we're approximating. Yeah. Okay. Okay, so just to summarize our results, we come up with new tighter bounds for the IID unit demand setting with m buyers, m items on this gap. When there are more items than buyers, we give a constant 1 minus 1 over e bound. When there are fewer items than buyers, we give a log n over m bound, and then we prove this is tight up to constant factors. Okay, so together that implies the tight 1 plus log n over m bound. Yep.
Sorry, can you say again what Ellis just asked and what your answer was?
Sorry, I didn't hear your question.
What was his question?
His question was, let me go back. His question was about this gap, welfare over utility, and the fact that they are both in expectation, right? They both have expectations around them. It's not instance per instance gap, it's expectation over expectation. And then I was talking about why we're bounding this gap, but I can repeat that in a few slides.
This is true for your result as well, or?
Yes. Same.
One more question. When
Yes.
you have more items than people, why don't you just give it to all of them at price of 0?
It's still unit demand. They still only want one item. So you still have to decide who wants each item.
Right, they're identical items.
No. Now we're in the matching setting.
Okay.
The identical items was what Heartline Rough Garden 08 did, but now we're in the setting where we have different items. So it's a matching setting. Yeah. Okay. Other questions? These are great questions. Okay, so why is this problem hard? I started by talking about the one item setting when you just had an apple, and I said we have solutions for all of these different things. What happens when you try to generalize to the setting with an apple and an orange? Okay, welfare generalizes beautifully. We go from the second price auction to the VCG auction, which is just basically a nice generalization of that. Not to be confused with generalized second price, but anyway. Great, so everything works out fine. We know how to implement VCG. Everything's truthful. You can get the optimal case. Great. What happens when you try to get optimal revenue for just an apple and an orange? Let's say we're unit demand. We have all these hardness results that say that the optimal mechanism is insane, basically. It says that there are uncountably infinite options, there can be, in the optimal mechanism. It's intractable to compute. The form of the mechanism basically looks like I have a lottery ticket. You pay me $5.19. I'll flip a coin with some probability PA for the apple and some probability PO for the orange, and you'll get each of them independently. But if you pay me 1 penny more, I'll give you a different lottery ticket with very slightly different probabilities for each of the apple and the orange, and I have uncountably infinite lottery tickets, all with very slightly different probabilities, so that whatever your value is, I'm getting you to pay exactly your value so that you can have slightly more probability of getting the apple and the orange. Okay, and so it's hard to reason about, it's hard to compute, it's too many options, and we still know very little about this mechanism except for that it has this unwieldy format. Okay, so obviously we can't implement this in practice, we can barely describe it. We can't do that. So what has been done in practice is instead using simple mechanisms to approximate optimal revenue. For example, what are the two simplest possible mechanisms? Say we're trying to sell a bunch of Microsoft services. We could price Excel at some price, and we could price PowerPoint at some price, and you could buy each one of them separately. We could sell them separately, or we could price them all together in Microsoft Office, and you could buy the grand bundle. Okay, so either price them separately or price them all together. Those are basically the two simplest mechanisms, and what a ton of results that I didn't have space on this slide for have shown is that for many, many different settings, the better of these two mechanisms for any distribution gives a nice approximation, gives like a constant factor approximation depending on the setting. Okay, so what we want to do is utility is going to be in a similar case to revenue, which if I have time at the end, I'll talk about why. And so we want to try and take this viewpoint of let's come up with simple mechanisms that give some approximation. Okay? So what simple mechanisms can approximate optimal multidimensional utility? That's what we're going to try and do today. Okay? So what do we know about utility from the one apple setting where we actually know how to solve things? In those extremes, depending on the distribution, we either have a second price auction or the lottery. By lottery, I mean it's free and you just give it away at random. Okay? Are these good mechanisms? The lottery is great because it's a free price. We don't have to subtract anything off of the objective. But why, if we have an apple and an orange, are we giving stuff away completely at random? If we have two different people and someone prefers the apple and someone prefers the orange, we should listen to their preferences. We shouldn't just completely at random give it away. So there's a way to improve upon the lottery when we're now dealing in a matching setting. Okay, makes sense? Okay, when we deal with VCG, which I'm not completely explaining, but it's kind of like second price generalized, preferences are totally used in this case. But the problem is, if everybody has similar preferences, then the prices are really high. And so this is, again, sort of like the second price setting, where if the first highest bidder and the second highest bidder were really close together, then we had a really high price and we weren't getting much utility. Okay, so this is, again, a problem. And so the idea is, what if we let people express some of their preferences, like express their favorite item, and then we reduce to just one item mechanisms, which we know how to solve. Okay, So that's sort of the idea we bring here. And so the class of mechanisms that we use in our work is we call the class of favorites mechanisms. So here's a class of mechanisms. Each bidder announces their favorite item, and they point to it. They say, that's my favorite item. That's the item for which they drew the highest value. And then we just focus on that specific item, and we run some specific single item mechanism M, which is going to be an input to this mechanism. For each item, we run that mechanism on the group of people who reported. So for example, for that first item on the right, we have one person pointing to it, so we run M on the item on the right with the one person pointing to it. We have another item with two people pointing to it. We run M on that item with the two people pointing to it. Those are the people participating in that auction. So these are now separate auctions. We have another item that people are pointing to. We run separately an auction for that item. So these are now one item auctions. Okay, we're in a one item setting. Make sense? Questions? Okay, what are the mechanisms that we use? We use two different mechanisms. One is just the lottery, uniformly at random. The mechanism just going to allocate randomly for free among the people who point to it. Okay? So we already said lottery is really great because it charges for free, but it didn't take into account that some people want the apple, some people want the orange. Now we've resolved that. You pick your favorite, and now among the people competing for the favorite, we give it away randomly for free. The other one is going to be a mechanism that I'm lifting from Heartline Rough Garden, which is their single item prior free mechanism. Again, by prior free, I mean it gives a guarantee for each instance. Okay? And we're going to use this in the case when there are fewer items than bidders. For the purpose of this talk, I'm going to hide the mechanism because it's not necessary, but I'm happy to talk about it afterwards if you want to talk about more of the details of this mechanism. Okay? So why is this incentive compatible? Why is this Bayesian incentive compatible? So over the fact that you know that people are drawing their values from distribution and reasoning about the fact that people are drawing their values from distribution. Any ideas? Why do you want to report your true value? So here's what we know. We know that the individual mechanisms we're using are Bayesian incentive compatible. But why is this part where we point to each item and then use that mechanism Bayesian incentive compatible? Yeah.
Can I say why I'm confused?
Yeah.
Why it is?
Yeah.
Which I don't see like why if like everybody loves one item and there's like a second item that you only like sort of like. If everyone piles onto that one item, you'd rather just participate in the lottery for the second item. So it seems to me like you should.
Totally.
You'd rather point at your second item than your first item if there's lots of contention.
Totally. If everybody loves the apple, I'd rather point to the orange so there's less competition. But what setting are we in? We're in an IID setting. And that's the key, right? The key is that over the draws of the distribution, equally many people should prefer the apple to the orange. And that's exactly it, right? So by IID-ness, in expectation, every item should have the same number of people who prefer it and thus compete for it. Exactly right. Thank you. And so also because we have the same priors, because of IID-ness, everything is getting the same input as well, right? Like it's not like the apple is getting different people competing for it because they all have, in expectation, the same distributions competing for it. So everything will be nice and truthful. So this is like a very crucial observation, is that in this generalization where we generalize to this IID unit demand setting, you have this really nice symmetry so you can break it down into these pointing to the items, and then everything is going to fall out really simply. Okay, so let me get into these actual cases. And now that we have made these observations, like this is really my favorite part of the paper, is that a lot of it is sort of making observations about the setting that get you down into such simple settings that I can show you the proof. Okay. So now we're in the setting where there are more items than buyers, and I'm going to show that we get 1 minus 1 over E approximation. Okay, so let's start with a case. Let's suppose that the number of items equal the number of buyers. So we're in a matching setting. When is an item not allocated? An item is not allocated only when it is not any agent's favorite item, right? So if an item is not any agent's favorite item, what does that mean? That occurs with probability 1 minus 1 over m to the n, right? Because everything is IID. Cool? And because n equals m, a bidder is not allocated in the same event. Make sense? So then the probability that an item is allocated is just 1 minus 1 over m to the n, which is at least 1 minus 1 over e, because n equals m. This is beautiful. Okay, but I said this isn't the case where m is at least n. Why does this improve? Well, as m grows, the probability that an agent is allocated only increases. That's it for this case. Okay? And that's why just allocating uniformly at random totally works here. Any questions about that? Okay. So what about the case where we have more bidders than items? Okay. So this case is a little bit different. Here we're going to have to use this prior free favorites as our wrapper, but I'm actually not even going to have to go into the details of that because I'm just going to take the guarantee out and black box it. Okay, so in the case where in item J, we're going to talk about when n prime buyers are competing for it. So for an item J where n prime buyers are the ones who prefer it, who compete for it, let's say capital V is the highest value for item J among everybody. All bidders, not just the ones competing for it. If the person who has value V is also competing for J, then Hartline Rough Garden tells us that the single item prior free mechanism, the one that we're using on this item, gives us a guarantee of V over 2 times 1 plus log n prime. So it's in this V and the n prime, the number of people competing for it. Okay. The question is, what is the probability of the person who owns V competing for this item? Okay. So we know that V is the highest value for J. So in some sense, V, the bidder who has V is J's favorite. It's the item's favorite bidder. And the question is, when is J also that bidder's favorite item? So we're going to call that favorites aligning. Okay. So the probability that favorites align, that the owner of V prefers J, is at least 1/2 independently for each item J by the IID-ness and the fact that m is at most n. Okay, so this is just the fact that we have independent draws, and we're asking when is it max. Okay, makes sense?
Sorry, why is it half? Can you explain?
Yeah, so we're just asking, when does the owner of V, when does this bidder prefer J? Okay, so when do they have the highest preference for J compared to their preference for any other item? Okay.
Why half? Sorry.
So it has to be higher.
Right, than every other draw he has for any other item.
Right.
The event you're conditioned on is his draw is highest for the J's item among all draws for J's item.
Yeah.
So we're just talking about the number that's on these two, m plus n draws.
Exactly. Exactly. So it's m plus n draws, exactly. But also we have that m is less than n. Yeah, exactly. Okay, and then also something I'm going to hide is that we have a technical lemma that shows that basically the correlation is nice. So basically if we have the expectation of the fraction, this is at least the expectation over 1 plus log of the expectation. So we can put the expectation into the numerator and denominator. And this works out because these are nice types of random variables. We're basically dealing with like binomials and stuff like that. So because of this, we can then put this in to our approximation and say, we're getting this guarantee. So when we have this with the probability at least 1/2, we get this in this case. So in this, so in expectation, when we get this for each item, this combines to give us this approximation. Right, so we're getting this for each of the items J. So for all m of the items J, we're getting it with probability 1/2, and then we combine it with our lemma. Good. I see confusion.
some point this n prime is turning into an n, and I don't totally understand.
Oh yeah, this is like in expectation, because you get to pull in the n prime into the expectation, n prime over m, and this is like the expected number of people competing for it in an IID setting.
Okay.
Yeah. So this yeah. It's just nicely divides. And this is why it's important to be able to pull the expectation in, and this is why we like need this technical lemma. Okay, cool. And so now we have our guarantees for the two different settings, and what's really nice is that we're able to then show tightness in this thing. Obviously the constant is tight for asymptotically. Now we can show tightness for this other setting as well. And the way that we show this as tight is basically they show this as tight in Heartline Rough Garden for the identical item setting, but that doesn't immediately apply to our setting because our setting has non-identical items, right? We have a bunch of different fruit as opposed to identical fruit. And so what we're going to do is we're basically going to find a way to create an identical items instance and then show that the gap goes in the right direction. So what we're going to do is we're going to start with our instance that has IID, unit demand, n buyers, and m items. And then we're going to transform it into an identical item instance, okay? And so the way we're going to start with our like matching instance, where you have values for a bunch of different items, and turn it into an identical items instance, is we're just going to say which item is your favorite. Say you prefer the apple, you have what the highest value for the apple. That's now your value for every item. Now you have identical values for every item, so you're treating them identically. Okay? Does the transformation make sense? Okay, so you start with different values. You have a value for the apple and the orange and the banana. You like the apple the most. Take your value for the apple, and let's pretend that's your value for everything. Okay? Where's my max? Okay. So then what they show in this HROA paper is that in this instance of identical items, this gap is true, that welfare is larger than utility by this gap. Okay? So then what we show is that we first show that in our original instance with different items, utility is only worse than in the instance where we'd make everything identical. Okay? And then we show that the welfare in our original instance C approximates the welfare when we take the max of everything. So because we show these relationships between the utility and the welfare, we can then show that because they have this gap on the instances of I prime, and we started with the instances of I, we then have this gap on I. Okay? Yeah?
Big picture question. So why is this opt welfare over opt utility ratio useful? Like, don't we care about the ratio between opt utility and utility that we actually get from the mechanism?
Yeah, absolutely. So basically, what we're doing in general is we're taking utility we get and we're comparing it to opt welfare because we don't really know what opt utility is. And therefore, we're getting statements about what this gap is and the fact that opt utility, how it relates to opt welfare, because we don't know what opt utility is. Okay?
We haven't done the other step yet of relating opt welfare to the utility that we get.
So that's what we did was we by showing one direction of the bound, we showed utility that we got certain approximations, right? We attain utility at least, yeah, and now we're showing that it's tight. Yeah, make sense? Okay, but this is a good point. Did you have a question?
Yeah, follow up to that. So then when you're solving, you would just solve for welfare and you make a statement about utility from there based on this bound?
So we're solving for the utility we get, and we're comparing it to the optimal welfare of the expected welfare of the setting, is what we're doing. Yeah. So this is a really good point, though, which is that we don't know about the optimal utility of a setting. And it took years and years of work in revenue in order to come up with good upper bounds on revenue in order to then approximate the upper bounds on revenue to get approximations to optimal revenue. We still don't really know what optimal revenue is. We just have pretty tight upper bounds on optimal revenue. Okay, that's how a lot of that works. We don't have good upper bounds on optimal utility at all. And the techniques we've been using for revenue are not working. So let me talk about why they don't work. Why is this problem difficult and different? Okay. I think I went into a little bit less detail here because I'm assuming you don't know that much about revenue and you don't want to hear the ins and outs of why the revenue details don't work, but let me talk about it at a high level. Okay, so in revenue, one of the things we do to try and understand the problems is we start with the one buyer M item problem as a foothold. We can prove hardness for this problem. Almost all of our hardness results are for the one buyer problem. We don't really have good notions of complexity for the n buyer problem. We always study the one buyer problem. That's pretty much it. We have menu complexity, we have hardness, etc. We also, all of our approximation results start in the one buyer problem, and then we figure out how to generalize them to the n buyer problem. Okay, for utility, the one buyer problem is trivial. What do you do when you have one buyer and any number of items? You just give everything away to them for free. When there's no competition from buyers, there's no need to charge prices. You can give them everything. Utility comes from the fact that there are multiple buyers. Okay, so using the one buyer problem doesn't work in utility. So we've completely lost that tool. Okay, and this expands really far. So if you're familiar, there's like all these really advanced heavy machinery tools of like using Lagrangian duality, but they all use the single buyer problem. All those solutions are for the single buyer problem and don't actually solve the multi-buyer problem. They use the single buyer problem. So none of this extends because we can't use the single buyer problem. Okay, the other thing is that competition hurts. Okay, so we always use the fact that competition helps revenue. So you get, for example, that copies is an upper bound, and we can use these sort of upper bounds to get better, in order to approximate revenue. However, copies is not an upper bound because competition hurts. So for example, if you were to take this setting where we have two buyers, the light blue and the dark blue buyer, competing for two items, say we're in the setting where one wants the first item, the apple, and the other one wants the orange. If you were to make copies of them, so what I'm doing is I'm making two copies of each buyer. One of them wants the first item and one of them wants the second item. They have the same values as each did for the apple and the orange, but now they're just separately competing, and you can even allocate multiple items to them. In revenue, this only helps because you're just giving more things away. You can make more sales. There's less constraints. But in this case, what happens is you're basically running two separate second price auctions now because there's no constraints. And here, even though they want two separate items, and so you could really just give them these two separate items and charge nothing, here you have to charge the second price in each setting. So you're actually going to have worse utility. Okay, so competition can hurt here. So the copy setting is not an upper bound, and competition actually hurts. Does that make sense? Okay. And in general, lower bounds can be misleading. So if you're trying to say, what's the lower bound for m? The lower bound for m is always going to be as bad as the lower bound when m equals 1, because m equals 1 is actually the worst case in some sense. So the worst case, as sort of illustrated by this, is when everybody wants the apple. The worst case is when everybody wants the same item and there's no preferences for the different items. Okay, so the lower bounds are always going to match the lower bounds from the original one item paper, when really what should be happening is, as is our bounds, there's an over m. It should get better in m. And that's actually what this recent paper shows, is that if you have your distributions that show that the preferences are distributed, like in the ID setting, the preferences are definitely distributed among the items. Even if it's not IID, if there's some way that the preferences are distributed among the item with some parameter C, then you do better. You can parameterize that in C. So the issue is really when everybody wants the same item, but as they start spreading out their preferences among the items and there's less competition, then you do better. And also, to answer your question, optimal allocations defy intuition because sometimes we prefer not to allocate. Even though in the one bidder setting, we'd rather just give everything away for free, when we're dealing with multiple bidders, sometimes the prices actually hurt us so much that we would rather use the power not to allocate. So for example, hopefully this isn't too technical, but if we have a bidder who has a value v1 for the apple and v2 for the orange, and they prefer the apple, but we want to give them the orange because of the other bidder, then what we could do is we could charge them the difference, v1 minus v2, and that will make them actually want to take the orange. But the other thing we could do is we could just only allocate the apple with probability v1 over v2, which is the other thing that makes them prefer the orange. And depending on whether there's an additive gap or a multiplicative gap and what those gaps are, it might be better for our objective to go with a multiplicative gap and therefore not fully allocate the apple some of the time, which is a really weird thing. You would think that if we're trying to maximize this trade-off, that we would always want to fully allocate, and sometimes we don't want to. So it's very weird. So there's a lot of weird intuition here that feels really, really different, even if you're really, really familiar with welfare and really, really familiar with revenue. This is a very different problem, and there's a lot of interesting math going on here. So that's what I have. Those are our results again, and then just to summarize again the open problems, we really don't have good upper bounds. Here we're approximating welfare, but it is log off. We really need to do better, and the techniques, like the years of research we have on how to do better, don't seem to work here. So we need new innovation. So thank you.